Question 42 is on what we call U-substitutions. So U-substitutions is going to be very similar to the chain rule, except it's the opposite of the chain rule. So if I kind of take you back in time to first semester, when you had things like 3x squared minus 1 to the 15th, and I ask you the derivative, do you remember how you did that? You better. So you get 3x squared minus 1 to the 14 times 6x, right? I almost wrote 3x squared, 6x. All right, so we are going to do the same thing. Well, not really the same thing. We're going to do the opposite of that process using something called a U-substitution. Okay, do you remember W-substitutions in Algebra 2? Kind of like that. So we took things that had X and we changed them all into W's, and then it made it easier so that we could use W's. That's what we're going to do here. So when we look at this, we don't know really how to integrate this. But we're going to identify what would involve a chain if I was taking the derivative. So the part that involves the chain is that inside part, the 1 plus x squared. So usually it's kind of inside parentheses, under a root. It's usually like the sign of something, but not always. So we'll talk about the weird cases. So when I take the derivative of this, I write du equals 2x. And then we used to have du over dx. That's how we wrote a derivative, like the derivative of u in terms of x. What we're going to do is we're going to take that over dx and we're going to kind of move it over here. So we're going to have times dx. I know that seems weird. It's like if you had units that were meters per second, you're multiplying the seconds over. Okay, and then we look for things that we're going to replace. So can I replace everything? So this portion here that's under the square root, that becomes the square root of u. The part that's 2x dx, what does that get replaced by? Du, yeah. So we end up with the integral of the square root of u du. Now do we know how to integrate that? Sure, because we can rewrite it so we see it as a power, u to the 1/2 du. So when I add 1 to the power, I get 3 over 2. I put my 2/3 out front and I do my plus c. Almost the final step. One more step. What do you guys think we do now? Yeah, we put the x's back in. So now that we've done the hard part of integrating, right, we made it simpler so we were able to integrate, and then we put our x's back in the equation. So we're like, well, u is really 1 plus x squared. So I have 2/3 1 plus x squared to the 3 over 2 plus c. And that's our answer. And you can always check. So if I let that equal y, so don't write this part, but look at it. If I let that equal y and I ask for like y prime, the derivative, do you see how we do 3 over 2 times 2/3? We'd have our 1 plus x squared. It'd now be to the 1/2 multiplied by our chain 2x. And these parts cancel. Do you see how we have 2x times the square root of 1 plus x squared? Same thing. So you can always check in the end if you want to, just to verify, but it should work. All right, so this is called the substitution rule. So it's basically when we take something that looks like the chain rule originally. Do you guys remember the chain rule when it was like f of g of x times g prime of x? So you guys remember if we had f of g of x for y, its derivative was f prime of the inside, I forgot my prime, times g prime of x, like that. That's what we're doing. So I need a prime there. Put a little prime in there. So we change it so that it looks something like f of u du. And then when we integrate, we get capital F of u, and so on. All right, so looking here. So I have x to the 4th sine of x to the 5th minus 4. What do you guys think the u should be? What's the inside part? Yeah, x to the 5th minus 4, totally. So when we do du, we say, well, that's 5x to the 4th, and then we tack on that dx on the end. So we start looking and we're like, okay, well, this part's replaced with sine of u. And then the x to the 4th dx, well, that's kind of there. So x to the 4th dx is 1/5 du equals x to the 4th dx. Do you guys see how I got it? Here was my x to the 4th dx. I divided the 5 over. I like for it to look like the part that I'm trying to replace. The 1/5. So it goes here with the d. So the 1/5 you can put inside the integration sign, like I could have put it in here as well. It doesn't matter. So the 1/5 can be here or here. I typically pull it out front, just so it looks nicer. You with me, Phil? He's looking confused.
Confused how you got the 1/5.
The 1/5? Yeah, so if you have, so you start looking for things that you're going to replace, and you're like, okay, that blue part is sine of u. So I definitely have sine of u in there. And then the part that's remaining besides that part that I underlined in blue is x to the 4th dx, right? And x to the 4th dx is kind of here, but there's that extra 5. So we divide by 5 on both sides. So we can write it as 1/5 du equals the x to the 4th dx. So we can say, okay, well, I'm going to replace that whole part in red, the x to the 4th dx, with 1/5 du.
I don't even know where the 5 came from.
Oh, it came from the derivative of x to the 5th, 5x to the 4th. Are you thinking integration? Are you thinking 1/6 x to the 6th? All right, anyway, so I have 1/5 the integral of sine of u du. So if I integrate sine, what do I get? Close. Negative cosine. So I have negative 1/5 cosine of u plus c. So it's negative 1/5 cosine of x to the 5th minus 4 plus c. The next one, u, 4x minus 5, du is 4, so we're going to tack on the dx. We don't have a 4 dx that I'm trying to replace, right? So what's my next step? Yeah, I would divide that 4 over, so 1/4 du equals dx. And I replace, so I have the square root of u replaces that square root of 4x minus 5. And the dx is replaced by 1/4 du. So it's set up so we are able to integrate. So I get 1/4 the integral of u to the 1/2 du, which is 1/4. When I integrate, I get u to the 3/2 with the 2/3 out front, plus c. So I get 2/12, which is 1/6, u, which is 4x minus 5 to the 3/2, plus c. Okay, does this make sense? All right, you guys try the next one. It's a little tricky, but if you can get this one, you'll be pretty good on the homework. Although there are going to be some weird ones. All right, so you should let your u part be the 1 minus 3x squared, right? Because it's kind of like the inside as if it was like the chain rule. So our du then ends up being negative 6x dx. And if you look for the things you're replacing, we definitely have like the square root of u on the bottom, but we're left with the x dx. So I would write it as negative 1/6 du replaces x dx, right? So we're gaining a negative 1/6. And you could put the du on top. Most of my students don't like that notation. Do you guys like that notation? If you want to think about the du as being part of the sandwich that kind of traps what you're integrating. So it's like the integration sign and the du kind of sandwich whatever the function is in there. You could do that if you want. So we get negative 1/6, and then we're integrating u to the negative 1/2 because it was on the denominator, so it's a negative power. So we get u to the 1/2 when we add 1, and we gain a 2, and then we still have that negative 1/6. So we get negative 1/3, whatever u is, to the 1/2 plus c. Okay. So I kind of write it like that sometimes where I just put a parenthesis because I'm like, okay, that's replacing the u. And then in one step I say, okay, well that's going to be 1 minus 3x squared. So that makes sense? Did you all get that? Awesome. All right, so what if you have sine of 4x? Any ideas on what your u should be? Yeah?
I have a question. So when you take like the
Antiderivative?
yeah, so you bring it down, so you multiply. Would you multiply by -2?
When you add 1 to the power, it becomes 1/2. So remember, if you are integrating like u to the 5th, you get u to the 6th, and you gain a 1/6 out front. That's what we're doing. So it's like a 1 over 1/2 becomes 2. It's like 1 over 1/2. It's 1 over the new power. All right, what's our u for the next one? Yep, 4x. So du ends up being 4 dx. So I have 1/4 du equals dx. So as I integrate this, I have the sine of u, du, and I have a 1/4 that I gain. So if I integrate sine, I get negative cosine. So negative cosine of u plus c times that 1/4. A lot of people get really hung up too on, like, do I put the plus c inside parentheses because I'm doing 1/4 of all of that? Right, if you have 1/4 c, that's still a constant. So I just kind of tackle on a plus c at the end, right? It's still a constant no matter what. So I get negative 1/4 cosine of the u, which is 4x plus c. So who thinks that they're smarty pants and can figure this out? What will this one be? If I integrate cosine, I get close. It's sine of the 7x, but you gain a 1/7 from the u substitution plus c. So it's not negative sine, right? Because I'm integrating cosine, which becomes positive sine. Okay, what if I had, what's it going to be? Nope, negative 2 cosine of 1/2 x plus c. Exactly, because you'd have 1 over the 1/2, which becomes 2, right? So it's kind of tricky. So some of these, like these sine and cosine ones, you can probably do without writing out the u substitution step. You just know that you're canceling the chain, right? You're doing 1 over the chain. Now, if I had something like sine of x squared, though, and I was integrating that, I can't be like, oh, it's going to be the 1 over whatever the chain was, right? 2x times. That's not how things like that work. You cannot do that for that. Okay, you'd have to do some kind of u substitution, which actually wouldn't work with u substitution because we're missing the 2x that we'd have to replace. Do you guys see what I'm saying? So a lot of times when you have u substitutions, it's very obvious. Like if I had an x the 5th minus 4 in here, what did I need? I needed a 5x the 4th, or at least something with an x the 4th. Do you guys know what I'm saying? So if I have something that looks like the cube root of 2x squared minus 7, what power do I need for x on top? I need x to the first, right? Because when I do my u substitution, I need to be able to replace the x dx. Do you see how I would still have an x dx? Does this make sense? Do you guys understand what I'm saying? Now, can there be situations where we have other things? Yes, so we're going to talk about those situations as well. But kind of look for things like that. That's always like an indication that we're doing a u substitution when you can see it like that. Okay, so let's do definite integrals. So there's 2 ways to do definite integration with u substitutions. So we're going to start out with method number 1. All right, so method number 1 is to ignore those numbers. These are called limits of integration, these numbers. If I ever say limits of integration, it's the a to b. So we're ignoring the limits of integration, and we're just pretending that we just have an indefinite integral. So we're like, well, I know my u is going to be 2x plus 1, and my du is 2 dx. So I'd have a 1/2 du equals dx. I know I go kind of fast, but are you with me? Do you understand what I just did there? So as we replace, we have the square root of u. The dx is replaced with 1/2 and a du. I add 1 to the power, so I get my 3 over 2, right, because it was u to the 1/2. I multiply by the reciprocal of that out front. 1 over 3 over 2 ends up becoming 2/3. Plus c. So I get a 1/3 u, which is 2x plus 1 to the 3 over 2, plus c if it was indefinite. But this one's not indefinite. It had numbers. So then we say, well, it really had numbers. It's 0 to 4. So I'm really finding 1/3 of 2x plus 1 to the 3 over 2 from 0 to 4. You can put the plus c there, but remember when you plug in the 4 and you plug in the 0 and you subtract the 2, they're both going to have like a plus c in them, so they go away. Plus c and then minus c. Are you with me? And then we plug in the 4. So when I plug in the 4, what do I get inside parentheses? 2 times 4 plus 1. So 9 to the 3 over 2 minus 1/3, 1 to the 3 over 2. I end up with 27 over 3, which is 9. You could write 9 if you want. Minus 1 over 3. I typically keep it over 3 because the other one was over 3 as well. So I get 26 over 3. Okay, not overly hard. I think you guys probably understand that process. Okay, but there's a second method, and this, personally, I prefer the second method. So every time I do it in class, I'll probably do method number 2. So we should probably figure out what this is so you know what I'm doing when I do method number 2. Okay, so the whole point of this is to replace our variables, right? Replace anything that has x with u. Okay, this includes anything that has x. And these numbers right here, the 0 to 4, those are x values, right? Isn't that just saying on the axis from 0 to 4, you're finding some kind of area, right, under the curve? You guys remember that? Those are x values. So what we're going to do is we're actually going to change even those into u values. Okay, so we started out the same way. And we're like, well, I have 0 to 4, 2x plus 1 dx. And I would need to let my u be 2x plus 1. Du then would be 2 dx. So I'd have my 1/2 du equals dx. So see how that's the same first step. Okay. And as we start replacing, I have the square root of u, I have my du, and I have a 1/2. But as I said, these numbers right here are x values. We want them to be u's. Okay, so let's think about it. When x is 0, what is its equivalent u? U is what? 1. How'd you get 1? You're right, it's 1.
You plug it in.
To what? To the u
original.
equation, right? Do you guys see u equals 2x plus 1? If u is equal to 2x plus 1, then when I plug in 0, I get 2 times 0 plus 1, so I get 1. Move this down a little bit. What if I plug in 4? Yeah, 2 times 4 plus 1, so I get 9. So those numbers that were previously 0 to 4 now become 1 to 9. Do you guys see it? Trying to train myself. This is a teacher thing. Trying to train myself to do the 4 on top and the 0 on the bottom. So when you replace, it's like on the top and the bottom. Because I've always done it the opposite way. I do like the 0 first and the 4. Because in my head, I'm going from 0 to 4, right? That's what an integral is, starting at the x value of 0 and going to 4. And so I always do the 0 in first and then the second one. But then people get confused and put them in the wrong spot. So I'm trying to do a new thing. It's hard for me. All right, anyway. So here we go. So now that those are u's, we never go back. Those are just u values. We never go back to x at all. We just keep everything with u's. So when I integrate, I get 1/2. I'm going to have u to the 3 over 2 with a 2/3. And instead of going from 0 to 4, I'm going from 1 to 9, these u values. So I have 1/3, u to the 3 over 2 going from 1 to 9, which ends up being 1/3 9 to the 3 over 2 minus 1/3 1 to the 3 over 2. Have we written this before? Yeah, we just did that. That was right here. So our answer should be 26/3. Okay, personally, I think that the method number 2 involves less writing. You don't have to do the indefinite part first. You just keep everything as u's. We don't change back and forth between them. So let's try it on this one. Do you guys want to try it out on your own first? All right, try number 2. So let your u be 1 minus 4x and change everything into u's. All All right, so you should let your u be the 1 minus 4x. So then du is negative 4 dx, which is negative 1/4 du is equal to dx. Okay, so Lydia had a right idea, but she let her u be 1 minus 4x squared, and then she ran into problems because the du then was 1 minus 4x, the first, times negative 4, and she was like, well, I can't replace this. Like, that's not written anywhere else in the equation. Does it make sense? So sometimes when you let u be something, you're like, ooh, it doesn't work out. So then think about what else you can make your u. That will happen quite a bit, actually. It'll be kind of frustrating for you, I'm sure, at first, but you'll get better at it. All right, so here we have 1 over u. My dx is going to be replaced by this part, the negative 1/4 du. So I have a negative 1/4 at du. And then I need to replace my numbers as well, my 1 and my 4. What did I do? Oh, okay, 1 over u squared. Thank you. I'm going to give it to Claire because I saw her first. She raised her hand and then the rest of you blurted it out. All right, so let's do, 1 to 4. So let's find what each of those are. When you plug in an x value of 1 in here, you end up getting 1 minus 4, which is negative 3. And when you plug in 4, you get 1 minus 16, which is negative 15. So you should have negative 3 to negative 15. There are a lot of negatives in this problem. Did it get a little confusing?
Would it be -15?
Can you make it negative 15 and negative 3? Because technically that's the way we write it, like with the x-axis, right? We'd say, well, we start at negative 15 and we go to negative 3 and then we find the area, right? That's what we're doing. So to me, that looks more correct. But what happens when I replace, or when I switch those around? I have to make the 1/4 positive. So you could also say, or positive 1/4, going from negative 15 to negative 3, 1 over u squared du. I don't care which one you did. So did you guys switch it, or did you guys keep it the same? You switched it. Okay. So then when we're integrating, we have u to the negative 2. So we add 1 to the power, so we get u to the negative 1, which makes this a negative 1/4 again. So we actually have a lot of negatives again.
Okay, what happened to the, when you take the derivative of u squared, don't you have to have a 1/2 by?
I added 1 to the power, so it became negative 1, and then I did 1 over the negative 1, which became negative 1. Do you want me to write that out?
No, it's okay. I'm just getting lost because you did 4, and so I don't know which one. Okay,
Yeah, so you can flip it basically. Do you see the or part? So if you don't like going from negative 3 to negative 15 and you want to switch it, you just take this negative and it now becomes a positive. So. All right, so we have positive 1/4. Do I have positive? No, I don't. I've messed up my signs by trying to help out you. Okay, so I get negative 1/4. And I have 1 over u going from negative 15 to negative 3, which is negative 1/4, 1 over negative 3, minus a negative 1/4, blah, blah, blah. You know what I do sometimes when I see I have that negative 1/4 out front? I just do a big parenthesis. So then I just worry about plugging in the negative 3 and the negative 15 to just the part that has the u, which is fine. So I have minus a 1 over negative 15. So we get negative 1/4, and I have negative 1/3, which is, if I get common denominators, it's 5 over 15 negative, plus 1 over 15. So I get negative 1/4 times negative 4 over 15, which becomes 1 over 15. Did you guys get 1 over 15 for your answer? It's a lot of negatives. I know. I knew what I was trying to get to because I did it in the last period. So 1 over 15. So actually that one would have been easier if you'd left it from negative 3 to negative 15 because you would have had less negatives. But I let you go with what you wanted, so it's fine. All right, so sometimes finding what to make your u can be tricky. So a lot of people think that u should be 3x in this example. But if you let u be 3x, you still have a sine squared u, cosine of u that you're trying to integrate. So that's a little bit weird, right? So what should we let u be in this example? Close. Not sine squared though, just sine of 3x. Because isn't that really kind of in parentheses as well? It's sine of 3x squared. It kind of goes back to those double chain problems we had. Isn't that an inside part as well? And what's nice if I make it sine of 3x, what's its derivative? Cosine of 3x times 3, of course. You would never forget that times 3, would you? So we have 1/3 du equals cosine of 3x dx. And we look for all the different things that we were trying to replace. So do we see that this becomes u squared? This part here is replaced with 1/3 du. Have we taken care of everything? Yes, we have. So we're integrating u squared with a 1/3 du. So 1/3 integral of u squared du. So our whole reason that we did this is it makes it easier. We know how to integrate this one, but we didn't know how to integrate the first one. Well, we know how to with U-substitutions, right? But looking at it at first without doing a U-substitution, it would be difficult. So we do 1/3. If I integrate u squared, I get u cubed with a 1/3 out front plus c. So 1/9 our u value cubed plus c. And then last step, our u was sine of 3x. Looks like that. And some people in the first class were saying, can you write like sine cubed of 3x? Yeah, you could do it that way as well. All right. So I've told you, usually when you have these du's, you can kind of see or when you set u equal to something, you can see the du hidden in the problem, right? And in that case it was. You can see the cosine of 3x in there as well. But what's wrong with this one? It should make you uncomfortable when you look at this one. You should be like, oh my gosh, I don't want to do this problem. Does it make you uncomfortable? Think about what you think your u should be. 2x minus 1, but what's wrong with it? That is actually what it is u equals 2x minus 1, but the derivative is what? It's just 2, and what's wrong with that, Abby?
There's no x.
Yeah, like how are we replacing that x? So as we start doing this, we see that we have the square root of u, and the dx is replaced with du. Well, it's replaced with 1/2 du, right? But then we still have this. So as I start replacing, it's like, okay, I got my 1/2, I got my square root of u, I got my du, but then I have this x there. Ah, good call. So he's going to solve for x, meaning you go back to this equation, our let statement, and how do I get x by itself? I add the 1 over equals 2x, right? And do what? Divide by 2. So I can replace any remaining x's with something in the form of u. That's the goal. I want all of those x's to become u's. So I get 1/2 the integral of u plus 1 over 2 times the square root of u du. Okay. I want you to think about how to integrate this. Some people were having trouble with it in the first period. You can do this. My hint is I would probably just pull that 2 out and write 1/4 out front. So try to simplify it and see what you get. Are you guys getting there? So I would write it as a 1/4 out front, and then you have the u plus 1 multiplied by u to the 1/2. Do you guys see? So I'm going to bring that u to the 1/2 in. So I'm going to get a 1/4 the integral of u to the 3 over 2 plus u to the 1/2 du. So I have 1/4. Let's do a big bracket. And now I integrate u to the 3 over 2, and I get 2/5 u to the 5 over 2. And I integrate u to the 1/2, so I get 2/3 u to the 3/2. And then I'm going to have all that plus c. So your final answer, I'm totally going to run out of room, is 2/20, because I got to multiply this 1/4 in, right? So it's 2/20, which is 1/10. Our u, what was u again? 2x minus 1, so 2x minus 1 to the 5/2, plus 2/12, which is 1/6, 2x minus 1 to the 3/2, plus c. That's, does that make sense? Do you guys get that? Think about you for the next one. Hi.
Hi there.
How are you?
I'm just coming to hang a new core value sign.
Oh, okay, good.
In the classroom. Good.
We jazzed it up, huh?
Oh, yeah.
All right, so this next one, any ideas on what u should be? If it's secant of 8x, what do we need to have hidden in there? Secant of 8x, tangent of 8x, 1/8. This one, the u is just 8x. Yeah, it's like, why? Why is it only 8x? Because I know how to integrate secant squared x, right? Or secant squared u. Because I've taken 18 million derivatives drills, and I know that the derivative of tangent gives me secant squared, right? I'm sure that you have memorized this. So I get 1/24 tangent of u plus c. So it's 1/24 tangent of 8x plus c. And you can check, you can take the derivative, and you do get that. All right, what do you think is going to happen on number 4? It's just like number 2, where you not only, like, you're going to let your u be that x minus 2. Because we want it to be like the square root of u, so we can write it as u to the 1/2 and then distribute it in. But like distributing something that's the square root of like x minus 2, that would be weird. We don't do that. We want it to be a single term under a root, so we can write it as something to the 1/2. So our du then is dx. And we solve. So we're like, well, I got my square root of u and I got my du. But I still have this x plus 2. So we have to take care of that. So we solve for x and we say, well, x is u plus 2. So I have u plus 2 plus 2. Do you guys see it? Square root of u du. So what happens here? So we have u plus 4 times the square root of u, which is u to the 1/2. Do you guys see what I'm saying? Like when I'm saying that's easy to multiply in, we just add our powers. That's the goal. So we get u to the 3/2 plus 4 u to the 1/2, and we do know how to integrate that. So we have u to the 5/2 with a 2/5 out front, plus u to the 3/2 with a 2/3 times 4, which becomes 8/3 out front, plus c. So our final answer is 2/5. X minus 2 was u to the 5/2 plus 8/3 x minus 2 to the 3/2 plus c. That was intense. All right, mentioning a couple more things. So number 5 and 6 on the next page. On this one, we would let our u be x squared plus 4x minus 3. Our du then becomes 2x plus 4. This is almost what we want. We wanted x plus 2 times dx, right? So Abby, what are you saying? Yeah, totally. We're going to divide by 2. Do you guys see how we're almost there? If we just divided by 2, we'd have exactly what we want. We like when it's exactly what we want to replace with, right? We don't like the whole solving for x situation. So then we get the square root of u du, and then etc. What would u be for number 6? X minus 4. So du would be dx. What do we need to do in that situation? Solve for x. X is u plus 4. So as I replace, I get u plus 4 squared. I add the 4 over. u plus 4 equals x.
Oh, right.
So as I replace, I have my u plus 4 squared. That was the x, right? X squared. And then I have over the square root of u, du. Would you know how to integrate that, though? Can you still do it?
Yeah.
I think you can. What would you do, Cole?
You'd solve the top or simplify the top.
Yeah, it'd become u squared plus
Powers.
8u plus 16 when you FOIL it out. And this is u to the 1/2, and then you bring all of those in. Right, you could do that. It's not fun, but you can do it. Right, so you're trying to get it into a form that you can integrate. All right, we're going to stop there. Pass out your homework. I know we didn't get to the even and odd stuff, but that's fine. You don't need that for your homework anyway.